The third method to control the speed of DC motor is terminal voltage or armature voltage control. Okay, this terminal voltage or armature voltage control. So this is a common method of controlling the speed of DC motor. Okay, this method is highly efficient and stable and is simple to implement. Okay, the circuit shows the basic concept of this method. So the only control variable is the armature voltage of the motor, which is depicted as an adjustable voltage source. And based on this equation, when the armature voltage is reduced, okay, Vt is reduced, the no load speed also reduce. Okay, no load speed equal to Vt over K flux. So when the Vt is reduced, the no load speed also reduce. Moreover, for the same value of load torque and the field flux, the armature voltage does not affect the speed drop. Okay, the delta omega. Okay, this method can be obtained by the following. Okay, first, when the supply is AC, we can use Watt-Leonard schemes, okay, or transformer with steps and an uncontrolled rectifier bridge, or we can use a static Watt-Leonard scheme for uncontrolled rectifier. Okay, for the Watt-Leonard scheme, I have explained before in the chapter 1. And then, when the supply is DC, okay, we can use a chopper. Okay, as we know, chopper will change the DC voltage from low to high or from high to low. We can use a buck boost or buck boost. Okay, this is the example of the Watt-Leonard scheme, the circuit arrangement. Okay, and then, okay, so I focus on static Watt-Leonard scheme. Okay, it is also known as thyristor bridge rectifier circuits. And then we use to get variable DC voltage from an AC source of fixed voltage. Means that we use a rectifier circuit. So in this chapter, okay, in this subchapter, we will look on first single phase half control bridge rectifier, single phase fully controlled bridge rectifier, three phase half control bridge rectifier, and three phase fully controlled bridge rectifier. So what is the difference between half control and full control bridge rectifier? You have learned it in power electronics subject last semester. Okay, so this is the SCR or phase angle control drive. So by changing the variable, the firing angle, so the variable DC output voltage can be obtained. Means that we connect the rectifier at the terminal voltage. So we want to control this terminal voltage by control rectifier. And then we can use single phase for low power and three phase for high and very high power. Okay. So the line current is unidirectional, but the output voltage can reverse polarity. Hence, we can use two quadrant operation. And then four quadrant is also possible using two sets of control rectifier, as I discussed in chapter 2. Okay, or we can use a switch mode drive. Okay, means that we use a switch mode DC-DC converter. So DC voltage is varied by duty cycle. Okay, for switch mode drive, mainly used for low to medium power range. Okay, for single quadrant converter, we can use buck. And then we have a half bridge, which is a 2 quadrant, and full bridge if you want to operate in 4 quadrant. Okay, this is the block diagram of the thyristor and SCR drive. And this figure, okay, we use a separately excited DC motor. Okay, so this is the armature and this is the field. The armature is the terminal of the armature is connect to the 3-phase rectifier. Okay, and for the field terminal controlled by single phase rectifier. Here we have a speed control with current loop here. Okay, speed control with current loop. Okay, so this is the main operator for the thyristor SCR drive, and the variable DC voltage are obtained from SCR firing angle control. Means that the terminal voltage is controlled by this thyristor, and this thyristor is controlled by the SCR firing angle control. Okay, this is the operation is slow response, and normally field rectifier have much lower ratings than the armature rectifier. It is only used to establish the flux. Okay. Okay, first, single phase half control bridge rectifier. Okay, why half control? How to differentiate between half control and fully control? Okay, you look at this diagram. For half control, we use a 2 thyristor and 2 diode. And for fully control, we use all 4 thyristor. Means that all the 4 switch we can control. Okay, this is the waveform, and then the main important is this equation. So how to calculate the average output voltage of this rectifier? Okay, this is the point for average output voltage equal to 0.45 VRMS 1 plus cos alpha. So you can try to derive this equation by referring to this output waveform. Okay, here the VDC average output voltage is equal to the terminal of the motor. Okay, you look at here, the output of this rectifier is connect to the terminal of this motor. Okay, the second one is single phase fully controlled bridge rectifier. So this is the equation for the average output voltage here, equal to 0.9 VRMS cos alpha. Okay, and then we have a 3-phase half control bridge rectifier. Okay, the average output voltage is given by this equation, 0.67 VRMS 1 plus cos alpha. So then for the last one is 3-phase fully controlled bridge rectifier. Average output voltage equal to 1.35 V line RMS cos alpha.